Today we're going to discuss two-dimensional motion. So far, the only thing we've looked at are objects that travel in one dimension. So let's see how two-dimensional motion differs from one-dimensional motion. Okay? The first thing we'll look at is just compare these two ideas. All right? One-dimensional motion, like we talked about before, is when an object travels left to right, up and down. Okay, and it was an either-or kind of deal. Okay, they did left to right or up and down. When objects travel in two dimensions, they're traveling both left to right and up and down. Okay, so there it would have some path that looks something like this. Okay, notice that this object is traveling both left to right and up and down. Okay, so it has some kind of horizontal displacement and vertical displacement. Okay, for our purposes now, when we talk about vertical displacement, let's call that delta y, just so we can keep that straight from our delta x. Oh, we didn't talk about 3D. Objects that travel in 3 dimensions then would have that z component to it. Okay, so if you had this object traveling here, you had the delta y, the delta x, it would also have that delta z also. I know it's kind of a crooked line. That means that this vector would come out of the page toward you or go into the page behind you. Okay, so that would give it a third dimension. It doesn't add too much to it in terms of trigonometry, but it's just something we're not going to talk about. Alright, so let's look at this example of two-dimensional motion. We have a ball that's rolling at some speed as it rolls off of a table. Okay, we can see this traveling 2 dimensions because it is going both horizontally, and once it reaches the end of the table, it's going to start falling and go travel vertically. Okay? So this object travels, it's going to have a delta y or delta x for its horizontal displacement, and we're going to have a delta y for its vertical displacement. Let's think about the motion of the object here in these two directions. When it reaches the end of the table, what direction is it traveling? Is it traveling horizontally or is it traveling vertically? You're right, it's traveling horizontally. Okay, so what kind of velocity does it have initially if it's only traveling horizontally? Right, it only has horizontal velocity. So this velocity, when it's at this point here, is all horizontal. So that's a Vx. So if it's traveling only horizontally, what's its velocity in the vertical direction? Correct, 0. So the initial velocity, and we're going to put a little y there to help us remember that it's only in the y direction that its initial velocity, in this case, is equal to 0. Okay, once it reaches the end of the table, it's going to start falling. And what causes objects to fall? Of course, gravity. So we're going to have gravity that's going to pull the object down toward the Earth. Okay, 9.8 meters per second squared is the rate of acceleration due to gravity. What is going to determine, in this case, the time that our object is in the air? Exactly, the y direction. Okay, gravity is what pulls things down to Earth. So gravity is what we say. Gravity always wins. It's going to be what's going to pull the object to Earth. So in this case, the time in the air is going to be determined by the y component. Okay, so keep that in mind. So the velocity here is all x to start off with. Velocity in the y direction is 0. And then gravity is going to be what pulls it down to Earth. Our other example of two-dimensional motion is this kind of what we call parabolic motion. Okay? When we have parabolic motion, we have an object that's going to start off traveling in 2 directions. Okay? Notice it has both velocity in the horizontal direction and the vertical direction. We know that it has both because it's going to be traveling in 2 directions. Okay? So if we draw a little vector here to represent our x velocity, and we draw a vector here to represent our y velocity. Oops, wrong way. Okay, that's better. So as it travels through the air, think about what's going to happen in both directions. Okay, we said before on the last slide that Vx is what the velocity had initially, and that the only reason that it was increasing vertically at speed was because of gravity. Was there anything that accelerates objects horizontally? You're right, there's not. Okay, once we have an object in motion, we're not going to be accelerating it anymore in that direction. So as the object travels through, its horizontal velocity is going to remain constant. Okay, that's something to keep in mind. The horizontal velocity will remain constant throughout because there's nothing there to accelerate it. Okay, that was kind of at an angle, but you get the idea. Okay, so our velocity vectors in the horizontal direction, and all of our orange ones are this Vx. Okay, they're going to remain the same throughout. Okay, so Vx is constant. Let's write that up here so that remember. Vx, the velocity in the x direction, is going to be constant. Okay, so you're going to keep that in mind. Vy, we know, is going to do what? Exactly. It's going to decrease as the object rises, and then it's going to increase as it falls. So let's see if I can draw some velocity vectors here that are at a decent scale. Okay. Okay, now we're going to be going in the opposite direction. Okay, we'll be gaining speed in the opposite direction. See that we know. Okay. All right. So there's our x and y velocity vectors. Okay. Vy changes due to gravity. Okay. It slows it as it rises. So notice our purple vectors here. They're going from larger to smaller to smaller. At the peak, I didn't even draw one. Why did I not draw a vector in the y direction at the peak? Exactly. The velocity in the y direction at the peak is 0, just like on our last example for the object rolling off the table. What is the object doing in the y direction at the peak so that I know its velocity is 0? That's right, it's changing direction. Okay, the object is changing direction in the y. Okay, so it's changing direction in the y dimension. Okay, so it's going from going up here, and now it's going to switch to start going down as we go to the other side of our parabola. All right, so keep that in mind when you're solving these problems. That's something else that you can use when you're setting up and solving your knowns and your unknowns. That Vy at the peak, we'll get rid of that knot. That was not what we needed there. Okay, we can say that Vy equals 0 at the peak. Okay, so Vy equals 0 at the peak. Everything we've learned so far, our constant velocity relationship and our constant acceleration relationships, have only applied for one-dimensional motion. Okay, so when we're given an initial velocity that's in 2 dimensions, let's say that we have a velocity that's at some value and then angled some degrees above the horizontal. Let's say that's about a 30-degree angle, right? Okay. Let's say our velocity here in both directions is 20 meters per second. Okay, so let's say we have an initial velocity of 20 meters per second, angled 30 degrees above the horizontal. There's basically nothing you can do with that information until you break it apart into its 2 components. Alright, so we're going to take this and we're going to break it apart into a horizontal component and a vertical component. Okay, just like we did with our displacement vectors before. So if we have this is our, well, we're going to say this is V. Okay, so V overall is 20 meters per second. We can break V up into Vy and Vx. Okay, remember how we did that? We used trigonometry. Okay, Vy, if our angle is this angle right here, okay, Vy is the opposite side of our triangle. Remember that sine is our trig function that relates the opposite side with the hypotenuse. So we can say that Vy, and in this case we're going to say V not y for the initial velocity, is equal to V times the sine of the angle. Okay, so we use theta to represent the angle, so just a general form. that v naught y is equal to v, the overall speed, times the angle, or times the sine of the angle. Okay, Vx is the adjacent side to this angle. So the trig function that relates adjacent sides and hypotenuse is cosine. So Vx is equal to v times the cosine of the angle theta. Alright, so now we've taken this two-dimensional vector, which was right here, and we've broken it apart into two one-dimensional vectors, a vertical vector and a horizontal vector. Okay, and now, because they are one-dimensional vectors, we can use them to solve problems. When we solve problems, what I would highly recommend you do is use something called an XY table. And an XY table just allows you to keep your thoughts organized on paper based on what kind of variables you deal with. Okay, we have the X side and we have the Y side. Okay, this allows you to not make mistakes, such as allowing gravity to apply in the X direction. Okay, that would be a mistake. So by keeping your thoughts organized on paper, it allows you to keep your thoughts organized when you solve the problem. Alright, so let's say we have a two-dimensional vector, like the one we had before, and we want to figure out how to solve the information in our problem. Okay, Vx, we would say, is equal to v, the overall, times the cosine of the angle theta. We know that v naught y is equal to v times the sine of the angle theta. Okay, some other information. We know that Vx is constant. How many equations do we know for constant velocity? Right, we only know one. Okay, so the equation that you will always use on the x side is that Vx equals delta x over t. Okay, that's the only equation you will use on the x side, because it's the only equation that applies to constant velocity. On the y side, we know lots of other different pieces of information. We know the acceleration due to gravity is 9.8 meters per second squared downward. Okay, so on the example we had before, where our object was initially going upward, see how it was going upward? Okay, right here. We would have to make our acceleration negative because it's downward. Remember, the direction is represented by the sign. Some other information we know. We said before, on a couple slides ago, we said that Vy is 0 at the peak. That's some information that we could put into our XY table. We know that Vy equals 0 at the peak. That's something you may not use every single time, but it's always a good piece of information to have. Then you look at it, you see, okay, well, I have three pieces of information that I could possibly know. I could know what V naught y is, I could know what A is, I could know what Vy is. So that would allow me to solve for the time. And when we have our XY table, the only thing that can cross both sides is the time. That's the only thing that's the same on both sides is the time. Okay? Think of it like you did, like what you learned in biology about semi-permeable membranes. Okay, on a semi-permeable membrane, only certain things can pass through. If this is our membrane, the only thing that can pass through that channel is the time. All right, so don't allow yourself to have multiple things go through both sides. It's only time. All right, so we've looked at this. We've set up the table. Like I said, it is a mistake to not use the table. It will help you keep your thoughts organized and help you solve problems correctly. So now let's actually solve a problem. Okay? An archer fires an arrow that's at 50 meters per second, angled 30 degrees above the horizontal. Determine the time of flight and the range of the arrow. Range is a word that we haven't seen before. But what do you think range means? Okay, if you guessed the delta x, then you guessed correctly. So we're going to set up a little vector here, and I'm going to draw the velocity vector. 50 meters per second, angle 30 degrees above the horizontal. Okay? Then I'm going to draw my XY table. That's going to allow me to put in information to keep my thoughts organized. Okay, so when we see a vector that's drawn in 2 dimensions, we know that we have to break up that vector into 2 one-dimensional vectors. That's the first thing we do, okay, every single time. So we're going to say Vx is equal to v times the cosine of theta, and v naught y equals v times the sine of theta. Remember, we say Vx because there is no change in it. Okay, we don't say v naught x because there is no initial and final x velocity. It's the same throughout. We say v naught y, however, because the velocity in the y direction does change. So we're going to plug in to these two relationships, and I'm going to say that Vx is 50 meters per second times the cosine of 30, and V naught y is 50 meters per second times the sine of 30. Okay, so we're going to plug that into our calculators, and we're going to say 50 cosine of 30, which gives a value of 43.3 meters per second. If you did not get 43.3 meters per second, check your mode of your calculator. You may be in radians. Okay, on the y side, we're going to do the same thing, and we're going to get 25 meters per second. Okay, so for our vector over here, we're going to say that the velocity in the x direction is going to be 43.3 meters per second throughout, and that the initial velocity in the y direction is going to start off at 25 meters per second. Okay? Let's think about the other information that we know. We know that our object is going to be accelerated downward at a rate of 9.8 meters per second squared. Well, because our velocity is upward and positive, we have to make our acceleration negative because it goes downward. All right? There's the first thing we know. They want us to solve for the time of flight and the range. Let's figure out which one we need to solve for first. The equation for the range is going to be on our x side, because remember, range is horizontal displacement, and we only know one equation on the x side. The x velocity is constant, so we're going to use that Vx equals delta x over t. We know Vx. Okay? We're trying to solve for delta x. What else do we need to know? We need to know the time. Okay? So we're going to try to figure out a way to solve for the time so that we can solve for delta x. We're going to use our y information to do so. All right? The piece of information that you don't have listed here that I asked you to remember before was that in the y direction, at the peak, the velocity is 0. Okay? So if we draw a little parabola out here, we're going to see that that's going to be the halfway mark. Okay? That's the halfway mark of our trip. So we can figure out the time it takes for the ball or the arrow to go up, then we can figure out the time it takes to go down. So if we draw a little graph here, we can say that the time it takes to get there, we're going to call the half time, and the time it takes to get there are going to be the same. So we're going to use this information to determine what I like to call the half time, the time it takes to get to the peak. Okay, so the variables that we are looking at relating together are going to be these four right here: initial velocity, acceleration, final velocity, and time. Okay, and that relationship between those four variables is just our basic acceleration relationship. Vf equals V naught plus AT. Okay, so in this case, we're going to make it a little more specific. So for the Vf, we're going to change that to a Vy, and the V naught, we're going to make it V naught Y. But it's the same thing. Okay, so at the end, we're going to make, well, we'll get to that in a second. Okay, so if we say Vy is 0, and V naught Y is 25 meters per second, okay, plus A, which is negative 9.8 meters per second squared. And because I've made Vy 0, I'm going to make T 1 half. Okay? And so I can remind myself it's the time it takes to get to the peak. So I'm going to subtract my 25 over and then divide by negative 9.8. So 25 divided by 9.8 is 2.551 seconds. So the time it takes to get to the peak is 2.55 seconds. Okay? The total time is equal to 2 times the half time. So I'm going to multiply 2.55 times 1, and I get that the time that the arrow is in the air is 5.01 seconds. So the time it takes to go from here and then go through the air and come to the ground is 5.10 seconds. Now I'm going to take that time and I'm going to plug it in on my other side. Okay, remember, that's the only thing that can cross the boundary is the time. We know that Vx is going to be 43.3 meters per second. So I'm just going to use the equation that I just wrote above. So that Vx equals delta x over the time, which was 5.10 seconds. I'm going to multiply both sides by 5.1. And 43.3 times 5.1 is 220.8 meters. So the arrow is going to fly 220.8 meters in the air. All right, so if you want to label that on a diagram, on our parabola, if we were to show this, okay, this distance right here is the 220.8 meters. Okay, our delta x is the range it takes to fly through. All right, so make sure you keep things organized. Make sure that you're not using gravity in the x direction, and make sure that you're thinking conceptually about the flight of objects in 2 dimensions. If you think about it conceptually and not just mathematically, it'll give you a much better level of understanding, and then the math will come much easier to you. Thanks!